An important part of materials engineering is not only understanding the inherent properties of materials in order to select the right material for the right job, but also how to manipulate those properties as desired by using chemical, thermal, and mechanical processing approaches. Ceramic materials are an excellent choice when high melting point, hardness, stiffness, chemical resistance, or insulating characteristics are needed, but they have a tendency to undergo unexpected brittle fracture. This fracture is usually a result of inherent flaws, such as pores or cracks, that arise during fabrication or use. Some of the typical strategies used in processing ceramics include reducing flaw sizes and/or porosity, avoiding sharp corners in part design that could lead to crack growth, and creating composite materials in which a ceramic is combined with a metal or a polymer to enhance toughness. Common examples are glass and carbon fiber composites, where the ceramic fibers are embedded into an epoxy polymer matrix. Polymers are inexpensive, lightweight, and easy to form into complex shapes, but they tend to have relatively low strength and stiffness, and they're sensitive to heat since they can soften and/or deform slowly over time, a phenomenon known as creep. Some of the typical strategies used to improve these characteristics include manipulating the length, alignment, and types of attractions between polymer chains, as well as combining polymers with ceramics to form composite materials with higher strength and stiffness. Metals have an excellent combination of strength, ductility, and therefore toughness, and so they're used in a wide range of structural applications. However, some metals tend to fail under cyclical loading conditions, a phenomenon known as fatigue, and others as a result of environmental exposure since they are prone to corrosion. Chemical strategies are typically used to prevent corrosion, often by forming protective surface layers or by including sacrificial adjuncts that protect the primary metal. The galvanizing of steel with zinc is one common example. One of the most important features of metals is that their mechanical properties can be customized to a greater extent than those of the other material classes. A combination of chemical, thermal, and mechanical processing can be used to carefully control the microscopic structure of a metal on various length scales, and to thereby tailor its strength, ductility, and toughness to some desired specification. We will spend a considerable portion of this course exploring the mechanical behavior of metals and the processing strategies that are used to control their structures and properties. As stated earlier, the objective of this lecture was to provide you with a broad but superficial overview of many of the concepts that we will explore further in the course. At this point, you should have a rudimentary understanding of the structure-properties processing relationship and how it applies to different classes of engineering materials. In particular, you should be able to list some of the differences in elemental composition, bonding, and atomic arrangement among the major material classes of ceramics, metals, and polymers. Should be able to explain how these structural differences relate to differences in properties such as density, electrical and thermal conductivity, melting point, stiffness, strength, and ductility. And you should be able to list some of the performance advantages and limitations of each material class, as well as some of the processing strategies that are commonly used to optimize material performance.